Find E at the origin if the following charge distributions are present. There's a point charge at a certain point, there's a uniform line charge, and then there's a surface charge. So basically what this problem's asking is we're going to incorporate all the different types of charges we've seen so far and kind of put it into one problem. So the first thing to do in this problem, I would say, is just break it up and do each one individually. So you do the point charge by itself, then the line charge, and the thing. So we'll start with the point charge. The first thing you want to do is write out your points, P of 206, and we're interested in the origin, right? Find E at the origin. So we'll call this P1, P2 is the origin. So we know that E of a point charge is going to be equal to whatever that charge is, 4 pi epsilon naught r squared over some unit vector of r, like that, right? So to find our distance, r is basically our distance between our point charge and our point of interest. So you just do P2 minus P1. So r would be 0 minus 2, negative 2, 0 minus 0, 0, 0 minus 6, negative 6. So E point. Plug in our Q, which is 12 nanocoulombs. 4 pi epsilon naught r squared. Put this in first, negative 2, 0, negative 6. This we can write as, it's a squared plus b squared. So we'll write that. We'll write this whole thing as r to the 3/2. You've probably seen this before, so this will be -2 squared plus 0 squared plus negative 6 squared. And these negatives are inside like that. And this whole thing is the 3/2. Okay, so you just do your arithmetic here. This is all now this is all known, right? Known stuff. So now you have E point. I got that equal to negative 0.85 in the AX direction, and then negative 2.55 in the AZ. So there's your first, that's your E due to the point charge, right? One thing you could do to make sure you have them slightly right, at least, is this should be, so this is a 2, this is a 6, so this should be 3 times larger. So if you do the math, that should be correct. And we'll leave this as 5, because that's what the book has. Okay, so next part, line charge. We will do this in a different color. So the line charge equation looks like this. Rho L, 2 pi epsilon naught R, these little r's, over times the unit vector. So it's almost the same thing, except for it's a line charge here, or not a line charge, like charge per meter. I'm escaping what it's actually called, but it's like charge per meter. It's not just charge. And then there's no squared on the r here, and then this is a 2. So there's a derivation out there. I'm not deriving it. This is just like know it. So now we find out what our R is. So just like the last time, we have our 2 points of interest. Our first point will be, it looks like -2, 3, and then we'll call that 0, even though it's really it's an infinite line charge, so we know we're not going to have a z component there. 0, 0, 0. You do the math here. That would be r equals 0 minus -2, 2, right? 0 minus 3, -3. And 0 minus 0, 0. And then you would bring that over here. Rho L is 3 nanocoulombs per meter. I'll just leave the meter out. Because we're not too worried about units. We kind of know what we're doing. This we can bring to, similarly like we did before, this will be an r squared because of the 2 r's. And it'll be a, you'll be squaring a square root, so we'll do that like that. So this will be 2 squared plus -3 squared plus 0 squared. And this whole thing is square root because it's the magnitude, right? And then that's squared. And then we'll have this up here too. Right, so this cancels with this. Epsilon naught over. So this is going to be a 4. This will be a 4. This will be a 9. And then you'll have your vector over here. This is more of arithmetic at this point, but I'll keep her going. 4 plus 9 would be 13. I can't make that straight. 2, -3, 0. And then this is going to equal, when you just do this math, you will get 8.3 ax minus 12.4 ay, and there's no z component. So there's no y component on the first one, there's no z component on the second one. And then lastly, we have a surface charge. I'll call it surf. And then our surface charge equation is rho s to epsilon naught. And then I guess before we actually do the equation, we should find out where the plane actually is and where it is relative to our origin. So at x equals 2. So if we have a graph like this, and our plane is going to be at x equals 2, right? Here's our point of interest, right? So if this is a positive charge, it would be pointing in this direction, and if it's a negative charge, it'll be pointing towards it. So we need to find out, we need to look and see. Okay, so it's a positive charge. You see there's no negative sign? So now we know that this will be pointing in the negative direction. Because this gives us the magnitude, but it doesn't really tell us the direction. So now we know that this will be a negative number. So 0.2 nanocoulombs to epsilon naught, that will equal negative 11.3. And know that I'm just throwing in that negative number does not come from this equation. That negative number comes from here. Because I know when we're going to add these all together, I have to factor that in, right? This equation doesn't account for that. So that's our 3. So now we have this part, and this part. And all we do now, we know all the things that are influencing the origin, the electric field at the origin. So we would just add those together. We'd add the 3 vectors together, and that's the answer. So E total is equal to, I'm just adding these numbers. AX. This is what I got when I added them. Minus 2.5 AZ. So again, I just took this, added them. Okay? There you go. Hope that helped. Bye.